if you followed my 4-step guide to drawing P&IDs, the first thing you do is draw yourself a P&ID map and figure out what you're going to put on the P&ID. So we kind of already thought that one through a little bit for you. You might want to move the borders around a little bit. That's fine. As long as we get all the P&IDs done, that's what counts. The next thing you probably will want to do is you probably want to have thought through the sort of top-down mass balance and flows around the process. So you probably want to just take a sheet of paper and just think through what are the major controls that need to be on there just to control the whole process. So feed flow control, maybe pressure control in a couple of places. So that's a good idea. Just do it with a PFD almost. That's good enough to get you started on it. And then you can kind of dive into the actual individual P&IDs. Now, I'm going to sort of quantify this. This is a lesson in drawing P&IDs, but there's going to be some stuff that we leave off these P&IDs. There's going to be a few things like line numbers and line sizes, specs that we're going to leave off on these P&IDs. So really, these are kind of a hybrid between what people will call a process flow diagram and a full set of P&IDs, or maybe just better referred to as a first draft set of P&IDs that the process engineers would work on. And then there's a whole bunch of other people that would get involved in the P&IDs and add a lot more information too. So with that kind of said, what we really need to do is we need to make sure that we've got all the inline instrumentation on the P&IDs, because our next step really is to get the pumps sized. And unless you know what the inline instrumentation is, you really can't get the pump size. You don't know whether you've got a flow meter in the line, and you don't know whether you have control valves in the line or not. We've got to get that under control. And so this exercise will do a very good job of getting that. It will also give you a really good sense of the controls that need to be on a full process. So, and we're not going to talk just about the basic process control. We're going to talk about the interlocks as well. So I think that'll be a nice little extension to your existing knowledge about controls. So the next step after that really is to think, well, we've got a certain number of pieces of equipment that we want to put on the P&ID, so we need to kind of organize it a little bit. This morning I got up and I thought it through a little bit and threw together a couple of just rough sketches of P&IDs, just mostly thinking about where I want to put the equipment on the piece of paper. And I think I was fighting with myself as to whether I want to put the steam drum on the left-hand side or the right-hand side of the reactor, and it probably doesn't make much difference in the end. So basically the first step then is to get a title block on the drawing here and start to lay some of the actual equipment onto the drawing. So let's put the major pieces of equipment on here. We know we have a reactor, so let's get that on there. And we'll just draw it kind of like a heat exchanger, because we know it's going to look like a heat exchanger. Like that, and like that. And we'll throw some tubes on there for now. We may want to come back and revise this a little bit later. A little bit of a tilt here. And we also know that we're going to have a steam side of this and a steam drum system. So let's draw the steam drum, and we'll put it here. Give ourselves a little, we want to get as much space here as we can, because there's going to be quite a bit of instrumentation on this steam drum. Okay. We probably want to put our normal liquid level on here. And we'll put our low liquid level on here for now. And we'll put a high liquid level, because we know this is a separator, so the high liquid level is going to be somewhere around halfway. So that seems pretty straightforward. The other aspects that we need to get in here are we need to put a cooler on, because on the next P&ID we go into the separator. So we're going to show ourselves a little bit of a cooler. And maybe we'll put it roughly here. This marker is not the darkest marker. I'm going to try and draw with it kind of sideways, then it gets a little darker. Like that. Now, you guys should have an equipment list, and you probably know what this equipment looks like. I suspect because of some of the temperatures involved, this may actually be a U-tube heat exchanger. So maybe we'll draw that as a U-tube heat exchanger. We'll just show a couple of little U-tubes in there just to make it a little bit more clear. And there's different conventions around how you're going to actually show equipment, but I find it really helps to show the pieces of equipment with a sense of how they're going to actually be built. Okay, so there's our cooler, and we're going to need some nozzles. So if you want to make the nozzles look really nice, then you can draw them like that. The other convention is to just draw them as a T. That, like that. And if you want to make them really cool looking, you rub that out and you make a little bit of an ellipse. And they look actually like almost real vessels. Oh man, this marker is going to cause me problems, isn't it? So if you do that, it just gives it a little bit more of an artistic look. Thus the art of P&IDs. Okay, so that's that. The other piece of equipment that we've got to get on there is, looks like we have a cooler going into the reactor for now. So let's draw that. We might not actually have space on here to do that, but we'll try and get it on there. This may be a case where we have to push it onto one of the other P&IDs. I will put it here. And it's pretty hot, so again, I don't know, did you guys, did anybody size that as a U-tube heat exchanger, or how did you, or a floating head, or how did you guys size that? Anybody remember? Should I just draw it as a U-tube then? It's the cooler going into the reactor. What's that called? Feed cooler or something like that? I can't actually see it on my drawing, so I think it's probably called the feed cooler. I'm going to draw it as a U-tube. There we go. Okay, so we have our reactor, our steam drum. Those are the two major pieces of equipment. Our feed cooler, let's put some nozzles on that. Wow. Does anybody have a better marker? This is really dodgy. It's the best one I have, but do you? Can I steal it from you? Is it better than mine?
I got one. I lied to you.
You lied? Haley's got one.
Oh wait, am I lying? No. I have a red one.
You got a red one? No, I want to use black.
Black.
Oh, there we go. Oh, that's.
It may or may not.
Those are usually good. Yeah, no, these are usually good. I lost my version of this. Oh, that's good. Yes, these are awesome. Thank you. Let's use your marker. I'll buy you a new one. There we go. That's what we need. Much better. Much better. Now you can see it. I'm just afraid the camera wouldn't even see it. Okay, better? Okay, that seems pretty simple, right? Do we have any more liquid levels we have to put on here? Not really. Do we have any more equipment? Do we have any more equipment? What do you guys think? Are we missing any pumps or anything like that? Let's put some nozzles on here while you guys think about whether we need pumps or not. Anybody see if we need any pumps or not? You gotta ask. You gotta be thinking about this game. What do you guys think? Any thoughts? We need a pump? What do we need a pump for? Pump water through the jacket? Okay. We might. Okay, so if we need to do that, we're going to need to put the pumps probably at ground level. We're going to need to put them in here. Okay. I think we can run the jacket with a thermosiphon. It might be debatable. But I think we can run it without actually having a pump. We just need to have the water, we need to have the elevations far enough that the liquid level in here is going to flow into the jacket of the heat exchanger. It's going to boil it and percolate it back up into the steam drum like that. So we don't need a pump for that. Do you think we need any other pumps though? What kind of pressure are we operating that steam drum at? Any thoughts? 700 what? 700 what was it? kPa? Okay, so I'm just going to write that down here. 700 kPa. And so that's 7 bar. What's the saturated steam temperature at 7 bar? 165. 165 Celsius? Okay. So if our process is at 220, right, that's roughly where our process is in terms of temperature, we're going to be probably a little bit too cold at 165. We probably need to be closer to about 200 degrees Celsius on the steam side, which is going to boost this pressure up to something higher than 7 bar. Where did the 7 bar come from? That's the boiler feed water. Right. Right. So we've got boiler feed water at 7 bar coming into the sheet, but we need to use it at 200 degrees Celsius. So that's going to be more like 10 or 12 bar or something like that. I don't know whether you guys have got the numbers handy or not. Anybody got HYSYS open? Check the exchanger operating pressure maybe. I'm not sure whether it's built into that mono or not. So I would say though that if we've got 6 bar coming in the sheet and we're trying to operate the steam system at 10 or something like that bar, we need some feed pumps in here. So my recommendation then is to put some pumps in here. And if you think about this, if these pumps fail and we lose our cooling water to the reactor, what's going to happen? What's the implications of losing cooling water to the reactor? The reactor's going to get extremely hot. Maybe. We could certainly damage the catalyst. Did anybody work out what the cost of our catalyst is in the last assignment? Over $1 million. Okay, so if there's a power blip and we lose cooling water, in a fairly short period of time, you're going to be writing a check for over $1 million. How many power blips do we get a year? Several. Could be writing several $1 million checks every year. That could be a bit of a problem. So what we might want to do is we might want to have an electric motor, and we might also want to have a steam turbine. To keep the pump running. So one pump with a shaft, electric motor on one side of the pump, and a steam turbine on the other side of the shaft. And maybe the steam system is a little bit more reliable than the electrical system. In either way, we could run one or two of the pumps on with a backup system. So the other thing you want to also do is you want to have two pumps. So because the pump, it could be a power failure, but it could be just a failure in the pump as well. So we would definitely want to have redundant pumps here. Can you follow that sort of line of thinking? Does that make sense to you guys? Okay. So whether we put a steam, we could get away maybe with putting a steam turbine just on one pump, but it might not be the best idea to do that. We might want to have a motor and a steam turbine on both pumps. So the reason you're going to have two pumps probably is you want to do maintenance on the pumps on a regular basis, and so you want to be able to flip those pumps back and forth, start one and run the other. I might rotate those motors and things like that. I have a good eraser here. I'm just going to use this. I'm going to move this stuff around a little bit. Oh, that's ugly. Okay. So let's put the motor in. And I'll put the steam turbine in like that. Okay. Okay. So that's, I think, all the equipment. Did I miss any equipment? You guys see any other equipment we need to have on there? So it's really just a question of piping it. Seems pretty straightforward. So we know we're going to have boiler feed water coming in the side of the drawing here. It's going to come in from a utility P&ID, so we don't need to show the drawing number for that because we haven't drawn the utility P&IDs yet. We've got our boiler feed water coming in here. Now, what you're going to find is the pumps. This one's kind of, these are special pumps because we're going to put steam turbines on them. But in general, when you put a motor on, when you put a pump and a motor on, there's like a kind of a standard envelope of stuff that's just going to basically come. My recommendation is maybe just draw one of those on some graph paper and then photocopy it a bunch of times. And then when you want to, when you're drawing your big drawings, you can just kind of move those around until you're happy with where they're placed. But the standard, sort of the standard controls here is to put motor control center in. That's shown with an interlock symbol, an eye, and a diamond. And I know this is kind of cramped down here, but you'll see why in a second. Okay, and then we need to have a local start-stop. So that's an HS in a balloon and a dashed line from the HS down into the interlock. So that gives us the ability to start and stop the pump and also to put it into auto. So we're going to write on, off, and auto. When it's in auto, that allows the DCS to start and stop it. On, off, auto, like that. And then we also want to know whether we want to be able to start and stop the pump from the computer control system, the DCS. And so we're going to put an HS with a box and a circle around it and a line through it, like that. So that gives us the basic controls for the electric motor there. Most of the time, in terms of the piping now, you'll want to know what the pressure is on the inlet to the pump. You'll want to know what the differential pressure is. So most people measure the inlet pressure by putting a PI in there. So we need to do that. So there's our pressure gauge, PI. Most of the time, the piping actually goes down a line size going into the pump. So you can show a reducer. Now, it's confusing that that looks like a turbine. It's not a turbine, it's a piping reducer. Like that. So that's going into the pump. And then if you start to work backwards, one of the things you probably want to have on your pumps is, well, we need to be able to switch between the pumps. So we need to put some manual valves like that. And it's pretty common to have some dirt in the water system during startup, so people will put a Y strainer in. And if you want to Google what a Y strainer is, you spell it like this. So put yourself a little Y strainer in your pumps. That will save you from destroying your pumps. And put a little valve on the Y strainer because you need to be able to drain the Y strainer. Okay, so we've got an isolation valve, a Y strainer. Sometimes people will put a drain valve in there as well, or sometimes they'll just drain off the Y strainer. And then a pressure indicator and then a reducer into the pump. And you're pretty much set for your pump. Now you come out of the pump and you want to put a pipe expander in, pipe expansion in. So that's just a reducer put in backwards. And then you probably want to know what the discharge pressure is on the pump, like that. So put a PI in there. And then generally you want to put a check valve in. So the check valve prevents liquid or water, in this case, from flowing backwards through the pump. That's particularly useful when you want to start the pump up. And then we need to put another block valve in. So it's another manual valve. And then we can join the pumps together. So then we're just basically going to duplicate that. We'll come back and do the controls on the steam turbine later, because they can be a little complicated. Like that. And we're done. Okay, so I kind of showed you the controls, the piping, and the valves all in one shot. That's kind of the block that you want to just carry around to different places. Now let's pipe the whole process here, and then we'll come back and do the controls and the rest of the stuff. Okay, so this is going to give us our water supply into the steam drum. So let's draw that in. And we're going to have to put some controls on this, but I'm going to draw the line and then just go back and erase it so I can put the controls in. Okay, so we've got water coming into the steam drum. The water is going to come down. Oops. There we go. Eraser doesn't work very well. And then this has got to come back into the steam drum, so we'll need to come in either on the top. Might as well just do it on the top then. Could come in on the side if we want, but might as well come in on the top. And we're going to do that. Pretty straightforward. We got to get over there. So we've got our syngas feed here. And that's coming from sheet. My computer shut down. What sheet is that, you guys, in the above? Sheet 3. Okay. You either give it a sheet number or just give it a different drawing number. Two different conventions there. Doesn't really matter. Okay, and that's got to go in here. We're going to come out here, and we got to get into that reactor there. So we got to weave our way around here a little bit. I think I'm going to cut it across here. And okay, so horizontal lines break vertical lines when they're major process lines. You could argue that this syngas is more important than the utility water, in which case it should break it no matter what direction it is. Okay. I'm going to go up here and break my way through this one. Then I'm into the reactor. Nice, if you want, you can throw a couple of little arrows on there just to help people understand what direction things are going. Just cosmetic, really. Voila. Okay, that's the syngas going in. Then we probably would have put the syngas on the shell side. Is that where you guys put the syngas? On that heat exchanger? Out through there. And we need to go off to, what sheet number is that? I think it's sheet 2 or 3 or something like that. So I get my computer, there we go. Sheet 2. The 3-phase separator. Okay, I kind of squeezed into my title block here. I'll move my title block later. Okay, so that's the syngas coming through, cooled through the reactor, through the heat exchanger, and away. We've got our boiler feed water coming in. It's coming into the steam drum here. It's mixing with the returning water, coming down, being boiled through the reactor, back through here. What are we missing? Are we missing any major lines? Cooling water, yep. Yep, we need some cooling water. So I think because it's a U-tube and it's horizontal, what I want to do is bring my cooling water in the bottom of the heat exchanger so it floods upwards and pushes any air out of the heat exchanger. So I'm going to do it that way. And I'm just going to go right off the sheet here. We're going to have to put some controls on here, so hang on to your hat there. That's that one. We're going to need the same thing here. I'm a little bit cramped in here, but I could draw it coming in through the sheet here. I could also extend that line down and pick it up. Let's try that, see if we can make that work. Definitely not going to have enough room for the steam turbine controls. That's that. And now this is a utility, and it's horizontal, so you would think because it's horizontal, it should be breaking that line, but because that's a major process line, we're going to break the utility instead. There you go. And I broke the utility around this one. Both of them are basically utilities, so horizontal is breaking vertical. Sounds reasonable. Am I missing anything else? Yep. Okay. What am I missing though? Vapor exit. Yeah, we got to get rid of the steam somehow. So let's put that here. To a steam header. Okay. Now do we have pretty much everything? What do you guys think? Did I miss anything yet? No? Okay. So now we need to work through our controls then, if we haven't missed anything at this point in time. Where should we start our controls? Let's start with the process maybe. So the syngas feed and the control system for the syngas feed is probably off the sheet. So, or it is off the sheet. So let's not worry too much about whether it's what the flow rate is, trying to control the flow rate. It's coming through, it's being cooled through this heat exchanger. We might be interested in what the actual temperature is going into that heat exchanger. Going into the reactor. So we probably want to measure the temperature here. We may not actually control. Changed my mind. We do want to control that. So let's put it a little bit closer to where we're going to put the controls for the cooling water. There's the TE there. We're going to put a TIC in. Like that. And then we need to put a control valve in to do that control. So let's put that in. Right there. Let's fail it open, because cooling the system off is probably a good idea in the event of a failure. Like that. And most of the control valves are a line size smaller than the actual pipe. So it's generally a safe assumption that you're going to need a pipe reducer on the inlet and the outlet of the control valve. It may not be the case, but you might as well throw it in there because it's probably going to end up that way. So there's a simple single input, single output control loop. You might want to give the valve an instrument balloon. So because it's on temperature control, then it's just basically a temperature valve. And we might be concerned with whether that temperature gets high or low. So we'll put a temperature alarm high and a temperature alarm low in there. It's conceivable that we want to isolate this from the cooling water. So we should probably put some manual valves in there. And I boxed myself out in terms of manual valves there, so, in terms of space. So let's see if I can erase that a little bit, move it around a bit. Like that. There we go. Okay, so that's easy. Let's keep on going. The next thing we probably want to do is we probably want to know what the pressure is into the reactor, because pressure is going to be an important factor in the molecular weight. So let's put ourselves, let's add a pressure indicating transmitter, put that into a pressure indicating controller, and somewhere that pressure indicating controller needs to control something. Two, and we haven't decided where that pressure control is going to come from, but essentially it's got to come from the system that is doing the pressure control for us in this whole big loop. And I'm going to leave that for you guys to think about a little bit, because there's a couple of different variables that need to be picked up to control pressure in the system. So that's that. We might even be interested in what the composition is. So if we have lots of money, we could put an analyzer in on that syngas feed. Put an analyzer indicator in like that. We may not control the process off it, but it might be really good information just to have in the control room. And if you want to indicate what we're actually going to be measuring, then you just put that beside it. So we might be measuring the CO and the H2 or whatever else we want to measure there. So an analyzer is probably not a bad idea in this particular process. Onwards and upwards. Coming out of here, the temperature might be higher or lower. So we are going to need to control the temperature coming out of the reactor. So we better measure the temperature, and then we better put a temperature indicating controller in, like that. And we most certainly want to have an alarm on that, probably high and low. And then we're going to have to send that signal somewhere. Where are we going to send that signal to, you guys? How are we going to control the temperature in the reactor? Thoughts? Dreams? The water through the reactor? Did you say, Rudy? Sorry, you just got to say it louder because I can't hear you over there. The flow rate of the cooling water. Kind of. You guys can read this. Oops. Q equals UA delta T ln, right? With an F factor in there if you needed it. Where does flow rate come into that? Because that's what dictates the heat transfer in a heat exchanger. Not the flow rate. Not directly the flow rate anyway. If we add more boiler feed water, we're just going to overflow the steam drum. Yeah, we could, if it got too hot, we could go back and we could say, let's reduce the flow rate of syngas, but most likely the pressure in the system would start to drop. Okay, so if we change the pressure of the steam drum here, then it changes the boiling point. If it changes the boiling point, it's changing the temperature. If it's changing the temperature, it's changing the LMTD of the heat exchanger. Bingo. So what we need is what? What do we need to do that? We need to measure the pressure. Okay, so let's get that on there. Let's put it here. Put a pressure transmitter in. Like that. So we got a transmitter. Now what do we do? Now what else do we need? We need to regulate the vapor flow rate out of here, exactly. Okay, so we need to basically put a control valve in, right? Like that. Do we want to fail it open or fail it closed? You think fail it open? Who thinks we should fail it open? Who thinks we should fail it closed? Only one person's willing to stick their neck out on this one, eh? Well, let's try it as fail open, and we can come back and look at it from a hazard analysis later on. So fail open by putting a little arrow sticking up there. Sorry, there we go. Tidy it up a little bit. Okay, what else? Okay, so we've got a valve. Now what do we need to make that actually work? We need a controller. Right, okay, so let's put ourselves, let's give ourselves a pressure controller here. If we can go from left to right in this situation. So this makes it fairly easy to read, hopefully. We need an electric wire going from the transmitter into the controller, and then an electric wire from the controller into the valve. Okay, that's good, but how do we relate that temperature? How do we get that temperature to control that pressure controller? So what we need to do, right, is we need to be able to adjust that pressure to anything we want. So the set point of that pressure, maybe it's 10 bar, maybe it's 12 bar, maybe it's 10 1/4 bar, whatever the pressure is. We want that pressure to be adjustable, and we want that pressure to be adjustable based on what the temperature is down here. Does that make sense? So what we need to do is we need to send a signal from that temperature controller to that pressure controller. What we really want is we want the set point of that pressure controller. So I'm going to put a little SP on there. And that set point needs to come from the output of that controller right there. And so since they're both in the computer control system, all we need to do is draw a software line. Piece of cake. We just need to figure out how we're going to wind it around, that's all. And that is called a cascade loop, you guys. Everybody see how that works? Makes sense? The other thing we might be worried about on this reactor is differential pressure. So if the catalyst is doing something funny, we might want to know that. So let's put a pressure differential indicating transmitter in with a signal into the DCS. So a pressure differential indicator in the DCS, like that. And we might as well just pick it right up off the reactor itself, like that. Put some valves in so we can isolate it if we want to. There we go. That gives us some insight into what's happening in the reactor. We know the inlet temperature, we know the outlet temperature, we know the inlet pressure, and we know the differential pressure across the transmitter. The only differential pressure. The only thing we don't really know is what the temperatures are actually in the bed. So it'd be nice to know what the radial temperatures are in the tubes. It'd be nice to know what the longitudinal temperatures are down through the reactor. We might want to try and do that. It's going to be really tricky to do though because it's a bunch of tubes, and we would somehow have to get a temperature element down into the tubes like this, and you'd probably want to pick off a couple of temperature elements like this. Problem is the temperature element, depending on how big the tubes are themselves, the actual temperature thermal well or whatever we're going to use to do that could kind of interfere with some of the flow rates, so it may not be super accurate, and the temperature elements are probably going to fail at some point in time as well. So, but anyway, you might want to try and do it anyway. Not uncommon for people to try and get some sort of temperature measurements into the reactors. That would take a long time to figure out how we're going to do that exactly because of the mechanical design of what we've got there. Okay, we got anything else? We come out of here, then we would need to cool it, and we're trying to hit, what did you guys optimize that temperature to? What was it? Anybody got an optimized temperature for the exit of that cooler? 65? Okay, so we need to measure the temperature. Now, one thing you'll see is I try and put the temperature element in an elbow like that because that's essentially how they're going to be installed. Here's a pipe elbow here, and they're going to put a thermal well into the pipe element, into the pipe like that, and then they're going to insert the TE into the thermal well, like that, and so that you have really good flow and good turbulence over the TE. So if you can, you try and show it on the P&ID like that. And we need a temperature indicating controller in order to do that, like that. We need some cooling water controls. It's cooling water, so let's fail it open. Actually, what we can do is come down here. There. Okay, so that's our cooling water. Let's put a manual valve on that and a manual valve on here. We might actually be interested in knowing what the cooling water supply temperature is and the cooling water inlet pressure. So we can put a PI, and there's a kind of a cool little device that actually combines a PI and a temperature gauge all in one. So that's kind of handy to have. And we'll just put that on here as well. If you had to, you just do it with separate gauges as well. PI, TI, like that. That gives us inlet pressure, inlet temperature, just in case you want to walk out to the field and just actually look at what the differential pressure of the heat exchanger is on the water side. Is that it for the process side? There's not much else we can really control here, is there? The flow rate control and the recirculation control is all done on the all done with the compressor. So if you want to actually control flow rates, you've got to go to the compressor P&ID and start to manipulate the way the compressor operates. So you'll have to probably take that P&ID that we did for the PHA, and a bunch of you guys noticed that the speed indicating controller on that compressor kind of goes off the page like this, and it goes somewhere else, and so you need to hook the controls up for that. Okay, so that's the process side. Now let's look at some more of the utilities here. The steam side, I think, is going to be a little bit complicated here. We know we have water coming in here, water circulating around through here. We might be interested in what the water temperature is going into the reactor. May not be something we're actually going to measure, that we're actually going to control off, but we might be interested in knowing what it is. Like that. We could, in theory, actually, if we really want to control that temperature there. No, we don't want to do that. I was going to say we could cascade it into that. We could control the water temperature instead of the process temperature, but it's better just to control the process temperature. It's more direct. So let's just make it an indication so that people can look at it anytime they want. It goes through the heat exchanger. Assuming there's not a lot of change in pressure here, it's just changing phase, so it's coming out of here to phase. Measuring the temperature isn't going to be terribly useful. You might want to do it anyway, but it should basically be reading the same temperature. So the only difference is the fact that there's going to be a slightly different pressure there. So you can put it in there. If they're different, then you'd probably start to wonder, you'd start to troubleshoot the process maybe. Okay, so that's kind of the water circulating around. We might be interested in knowing what the flow rate is. So if you've got enough differential pressure here, you could put a flow meter in. You could maybe try and find a very low pressure drop flow meter. So let's put a flow indicator in there. That might be useful just to know that you've got decent flow here. If you had a pump in here, you would definitely want to put a flow transmitter in there. So debatable whether we want to put a pump in there or not, but certainly we would have a transmitter in there. Okay, so now we've got the whole issue here is if we lose water into the reactor, it could be a very costly mistake. So we want to make sure that we always have water going into the reactor. And for the water to flow through that reactor properly, we've got to hold the liquid level at a fairly constant level. So right off the bat, we know that we need to have a level transmitter and a level control of some sort. So let's put that on there right now. We need a nozzle. Probably going to have some valves. I'll tell you right now, it's going to be a 3-inch nozzle. Okay, let's draw the level transmitter out here so we give ourselves a little bit of space. Okay, that's good. Now, the transmitter is all electronic. You may or may not actually trust the level transmitter. So you might actually want to put a sight glass on the vessel as well. That's pretty common in these situations. So we could draw the sight glass here, or we could draw the sight glass here. Sometimes people, if they're really cramped for space, they'll actually draw the sight glass right on the kind of on the vessel. It's a little bit confusing for some people, but I'm going to do it just to kind of illustrate how that would be sort of shown. So we'd show the nozzle like that. We'd show a valve like that. And a sight glass is an LG. So we do that. Come down here like that. And just drop kind of like that. So you can kind of see that it looks like a nozzle on the side of the vessel. It's just, I could have just as easily put it here because I've got lots of space there. Alrighty, now what? So we need to control the level. How are we going to control the level in here? How do you want to control the level, you guys? Thoughts?
We like connect like we connect like the relief valve to like the level transmitter.
You mean the pressure control valve?
Yeah.
No, because we've already got the pressure control valve tied up in an existing control loop. We'd end up with two controllers trying to get inputs from two different measured variables. That wouldn't really work. Any other thoughts? How about the feed water pump? If the level gets low, we put more water in. Good call. Okay, so let's put a control valve in here. Now, I want you to think really hard. In your experience of opening a pop can or a pop bottle, when you crack the lid on the pop bottle, what happens to the level? The level drops? Okay. Sometimes drops because you're drinking it. So all the gas starts to come out. What happens if you start to have that gas come out of solution though? What happens to the level? The level starts to rise sometimes for a little while, and then the level starts to drop again. It's like a dynamic thing, right? If we start to open or close that valve right there, we could expect maybe the level to initially, if we start to drop the pressure a little too quickly, we could expect maybe the level to rise a little bit, and then maybe for it to start to drop. It starts to drop because as you drop the pressure, we actually boil more steam right out of the steam drum. So there's situations where that level might actually be moving around, and that level transmitter might be measuring it, but it might actually kind of be a false level measurement. So we may not really want to respond to every little bit of blip in level there. What we might want to do is measure the flow rate here. Hold the flow rate fairly constant. So we'll put a flow indicating controller in here. And then our level indicating controller here can then send a signal down into the flow indicating controller. And if we really wanted to, we could even send a signal from the pressure controller down so that the flow controller knows that the pressure actually is being manipulated. And that's going to be a little complicated here. So we're going to cheat, and we're going to do that. And if you go and Google 3-element drum level control, you get more of the details of how that control system actually works. You can even write it down here. 3-element drum level control. My recollection of that control system is a little hazy. I think I've got it set up right, but we might want to go and just check, just to make sure I've got that right. I'll go have a look after class maybe, and if I make any mistakes, I can just revise them in red. That's pretty good. Now, one hazard we've introduced here is we probably want to. We may not want to fail that open. Actually, we may fail that closed. That might introduce some hazards as well. Or we fail it open. Well, let's just fail it open. I don't know, I'm changing my mind back and forth here. If we fail it open, then we might potentially create some serious hazards here, because we could potentially flood the steam header, and that's going to create some serious problems. If we fail it closed, then we could potentially lose water into the reactor, and we could potentially damage the catalyst at some point in time. This is a question of I don't think there's a right answer or a right or a wrong answer here. Either way, we are in deep trouble. What you could do, actually, here's something you probably haven't heard of: fail in last position. Fail in last position looks like this. That makes the control valve a lot more expensive. It's tricky to do that, but that might be the way to solve that. So I think that's the basic process control system. Did I miss anything? We're controlling the inventories in the system. So here's our inventory of water on the water side. Our inventory control on the gas side is really, there really is no control valves on the gas side. So the inventory is really the inventory of the whole loop. And that inventory control is kind of done with this PIT and PIC system and some other manipulated variable. The only thing maybe now to add is some safety systems here. If you've been listening to me talk the last couple of days, if that valve for some reason fails closed on us, we need to have a way to send that water back to its supply system so that we don't deadhead the pump. We don't want to have the pump just turning and putting power into that water and heating the water up. We want to send a small flow back. So we need to put what's known as a minimum flow bypass. And it's all basically here. Okay, so boiler feed water return. Okay, that's that. There's a couple of other things we probably want to put in here. You probably want to have a pressure indicator on here. So we can put it off here, put it off the same nozzle if we want. Like that. We know what the temperature is. Okay, so we know the temperature, the pressure, the level. We know what the flow rate in is. We don't have the flow rate out of here. We actually might want to know what the steam flow rate is. So this might be a case where you actually want to, you could create a cascade loop here. as well. And an FI in the DCS there. So we know what the steam flow rate is going into the header. That's a pretty common thing to want to know. We're not going to try and control the steam header pressure. We're just going to basically put steam into that header pressure, and the header has to basically deal with that pressure or else get rid of the steam somehow. Now what we need is probably some interlocks. We need some safety systems here. So if we start to get low liquid levels here, we could be getting ourselves into trouble here. So we might want to automatically start a pump up if the level starts to drop. So what we should do is put a level switch low. Let's make it a low. Okay, this will have a level alarm high and a low. And then that level switch low, we maybe want to tie into starting the pumps. So we're going to do that basically by tying the control systems in here. To the motor control center on the pumps. Like that. So that level switch low is now capable of starting the pumps. Probably a good idea. If we got to we might want to have a whole bunch of other we could have a low if we wanted to. So for instance, if we got to an even lower level, we might want to send that signal to an interlock to shut the syngas feed system off. We could do one of two things. We could actually isolate the reactor, stop the syngas going into the reactor by putting a block valve in here, or we could stop the compression system that's putting the syngas in. Another way we could do it is actually we could just open the vent valve on the purge valve and just dump the contents of the reactor out to flare. So I would call this the reactor shutdown interlock. I would put a note here. RSD, reactor shutdown. And then however we decide that we're going to actually do that shutdown, basically there would be another interlock like that on that other P&ID that gets that signal and activates it. Okay, so we've got a low level here. We've got a low. We might actually want to have a high level. We've got a high level just in software here. So that might be good enough. The only thing that's sort of unsatisfactory about this is the fact that everything is, you're trusting the level transmitter. So if the level transmitter fails for any reason, then you're in trouble. So you might be smart to do one of two things. You might be smart to put a couple more nozzles on here with level switches. Like that. And a level switch high. Like that. Level alarm high. Like that in the DCS. Low. And maybe what you would do is actually do the start-stop of the pumps based on these level switches instead of the transmitter. You could do it on both, actually. So you could easily, in the software, if either one of those basically goes low level, then like that. If either one of those low level measurements is detected, then we're going to start the second pump. So whichever pump is off, we're going to just turn on. Here's one thing that I would be interested in knowing is how much pressure those pumps are putting out. So I would put a pressure transmitter on there. So that if the pumps for some reason are not putting enough pressure out, we could be alarming on that, and we could be thinking about shutting the reactor down. Or even if we wanted to, we could prevent the reactor from starting up unless we've actually got boiler feed water pressure. That might be a smart thing to do as well. I think that's pretty much it. Oh, I know. Relief valves. Relief valves. We've got a potential levy hazard here. We need to make sure we put a relief valve on here. There. That looks a little bit confusing because it doesn't go into the steam line, it goes to atmosphere. To atmosphere. And that's our relief valve set at whatever our set pressure is. Okay, get rid of this. Not interested in what the actual operating pressures are at this point in time. It gets messy with controls, eh? When you start to really layer the controls on it. I think we've only actually probably just started this in terms of controls. I could see this getting a little bit more complicated through here. So if I was going to redraw this, I think I'd start to shift stuff that way a little bit and give myself a little bit more space on the P&ID. So that's why doing it on an 8.5 by 11 is a good idea, just to do a prototype of your P&ID. And oh, what happens in your kettle over time? It scales. Do you think we're going to have scaling in this system?
No.
Why not?
No, we will.
You think we will? Are you sure? 96, 97%, yeah? You bet your career on it?
Yes.
You would. Who else wants to bet we're going to have scaling or not have scaling? I think we're going to have scaling. What are we going to do about it?
Use like a scaling meter.
A scaling what, sorry?
Like a scaling meter people.
Yeah, we're going to have that boiler feed water is going to have lots of chemical treatment in it, but no matter what, you still potentially have some scaling and some solids build up and things like that. You can't possibly have completely pure water. We're basically going to pour thousands of pounds of water in here per hour. We're going to boil it out of steam, and we're going to be left with the solids that came in with that. So even if there's parts per million of solids, that's going to build up over time. That's going to be a problem. So what do we do about it? Thoughts? A water softener? This water is already soft. This water is as good as you can get it. You're going to do what? A manhole? Not a manhole, no. No, there'll be a manhole on the vessel, but that's not a way to treat to handle the possible water that's going to scale. What do you guys think? You're chemical engineers. You can problem solve your way through this.
If we like increase the temperature, would that like keep it as liquid almost?
No, actually, increasing the temperature tends to cause stuff to scale out more. The solubility usually goes down with higher temperatures of some of those. Decrease the temperature, yeah, but the temperature is being controlled by the reactor. You don't have any choice over the temperature. Any other ideas? You're thinking about it at least. What else can we do? Shut it down and clean it? Yeah, okay. Could do that. Might have to do that. Got any ways we can do it kind of continuously? Anti-scaling. That's already built into the water coming in here. It's got a nice chemical treatment system, but still, it's not good enough. What else can we do? No? Can you design it for scaling? I guess you could sort of design it for scaling, but what can we do to try and get rid of those solids? Get rid of that solid buildup, that scale buildup.
If we like vibrate the tank, could that like get rid of like buildup?
Maybe. Maybe. That's going to be tricky though. This is going to be heavy stuff. That's going to be heavy stuff. Where do you think this stuff would be? In the bottom, yeah, it might be in the bottom here. That's true, yeah. It might be kind of circulating around as well, right? Yeah. Well, what do we do? Yeah.
We put like a filter or something, like some sort of like screen or something that we can clean up.
Yeah, we could put a filter in maybe. Yeah. Yeah, we could put a filter in. Okay. Like where would we put it?
Maybe on the tank.
Going in here? Yeah, but that water's pretty clean going in. Michelle, you got some ideas? A manual drain? Okay, we could put a manual drain on there, yeah. What are we going to do with the manual drain? Just like have a bucket there and... You got to say it a little louder, I can't hear you, sorry. Now let's make it small. A drain. A drain. So how's a drain going to help us here? So just a purge for the liquid. Okay. And then we send it where? We gotta get it out. We gotta get it off the sheet somehow. That's gonna be tricky. How about if we go through here? And because it's kind of a utility, not a process, we're going to break it that way. This we're going to break like that. Okay. How do we put a manual valve on that, or what are we going to do? How do we, if we just leave that like that, then there's going to be no water in the tank, right? It's just, whew, it's gone. So what do we do? Put a manual valve on? Okay? Like that. And then how often do we know when to how often do we know when to open it or close it? Just a basic level gauge. Well, the level's here, right? So yeah, I mean, you could drain a little bit off, except that the level would probably refill as fast as you can drain it out of there.
Can we not see it through like the glass?
Can you see you see the solids, you mean, or see the level? You might see the solids. I doubt you'd see the solids because you really don't want to have that many solids in there. You could be measuring conductivity, yeah, because the conductivity will go up as you have dissolved solids, yeah. So we could put an analyzer in there on conductivity. So we could basically put a nozzle in, or we could pull it off here. Let's pull it off here maybe. Analyzer element, conductivity, analyzer indicator, conductivity. Yep, we could do that. Missed a line. Okay, now, okay, so if we're going to do that, we might as well make it a controller, right? What are we going to control? What should we control? How about flow rate? Okay, that's messy. Let's just fix it so it looks prettier. Oh, God. Like that? Okay, so now what you can do is you can say, based on conductivity, we'll just basically purge more water out of there. And this has a technical name. It's called blowdown. The only problem is there's quite a bit of heat in that water, so you might end up, if you start to get clever and start to think about this, you might actually want to put a heat exchanger on there and maybe preheat water with it, because you can imagine that's one of the energy losses in a system like this. Do we miss anything else? I think that's probably it.